So it's great to be here. I'm going to talk about the work that I've been doing that's been ongoing with the Kinsey Institute. And I began working with the Kinsey Institute some years ago to look at, how to create a system for them to do longitudinal studies and protect the data that they collect. And so they were more concerned with protecting data while it was stored. And so when I began to talk to them about the types of data that they have, it became clear to me that there were a lot of other issues that they were not considering. So one of the things that's driving this work is that now their funders are asking them to have a data sharing plan. And so they don't really know what it means to share their data and what risks there are inherent to the data set that may lead to the re-identification of individuals within their data set. So I'm not sure if you're familiar with the Kinsey Institute, but Alfred Kinsey actually started the Kinsey Institute, and he did a study of male and female sexuality, I think around in the 30s or 40s. And so a lot of the data that they collect is extremely sensitive. They're also very concerned about their data being subpoenaed, not just, okay, I lost a data set and maybe someone gets a hold of it and someone's re-identified, but they're also very concerned about subpoena of their data. And so one of the things that I'm exploring with regards to looking at this issue of utility is there at any phase we can get rid of the original data set and actually use a noisy data set all the time, given the types of things that they want to do with the data set. So that's one of the questions that I'm trying to understand where we are. So this talk is about evaluating the utility of a behavioral science data set. And my collaborators are, the graduate student is Mike Hansen. He's done a lot of coding. I call him my code hustler. Kinsey, Julia Hyman is the director of Kinsey. Stephanie Sanders, she's the PI on the grant with me that this work is funded under. Eric Jansen is also another researcher. He was the primary researcher at Kinsey that collected the data that I'm studying right now. And Li Zhang is a professor at Emory University, and she and her students designed one of the algorithms, differentially private algorithms that I'm working with. So usually I start by talking about what the title is. And with regards to a differentially private data set, at this point in the talk, just think about differential privacy being some type of sanitization technique. And the goal is to limit the likelihood that someone can be re-identified in the technique and re-identified in the data set. And so that's all you need to know about differential privacy right now. I'll get a little bit more into it when we talk about the algorithms, but just think of it as a sanitization technique. So I'll talk a little bit about re-identification, certificate of confidentiality, and forced disclosure, because these are the kind of things that the Kinsey Institute is concerned about. I'll talk about differential privacy, and then I'll talk about my methodology for evaluating utility, which is kind of like one of the main contributions of this work. I'll give you some of the results, and we'll talk about conclusions in future work. So the scientists at Kinsey, all of them are psychologists that I'm working with. And so the data that they collect, it may be medical related data. So that's another reason that we're really concerned about, someone actually being able to re-identify someone in the data set. So when I say re-identify and I say data set, the data sets that they collect, they don't retain things like your name in the data set. They don't have your zip code in the data set. They don't have your birth date in the data set. They may have your age. They do have gender. Okay, so what we know about re-identification is that anything that makes you unique may likely be used as a quasi-identifier, and you can use those unique characteristics possibly and link it to an external data set, and then that has your name, and then re-identify you. So I'm talking about re-identification, but that's what I mean. So, and if we can do that, then Kinsey is concerned about damaging a person's reputation because they collect extremely sensitive information. And so I talked about the funding agencies, and also there's this whole issue of data sets being subpoenaed. One story that the researchers at Kinsey always talks about is that of spouses going through divorce, one spouse actually knowing that the other participated in the study. This study discusses something about infidelity, and they want to subpoena the actual data set in order to prove their claim of infidelity. That's one particular example. So with regards to certificates of confidentiality, and I think this is related to like health-related information, but the Kinsey Institute, because they collect this self-reported medical information, they can get certificates of confidentiality, which is a federal statute about whether this data can actually be subpoenaed or not, and protect studies against subpoena in court. But this has been challenged in court. There's one particular case that I was looking at in North Carolina where there was someone who was on trial for some type of attack. There was a witness who had participated in a study at Duke University, and this witness, the defense attorneys actually wanted to subpoena those study records to determine whether they could actually discredit the witness. And so although the study records were protected by a certificate of confidentiality, the judge eventually allowed the defense attorneys to have access to this data. Limited access, but access. So although the study records were never put into public record, the certificate of confidentiality did not protect it from someone outside the study having access to this data. So this notion of compelled disclosure is a big concern for them. So that kind of motivates why we're looking at this. We want to protect an individual within a data set. We don't even want you to know that the individual is in the data set. And so this is one of the reasons why we're looking at differential privacy, because the promise of differential privacy is by allowing and sharing your data set with, your data within a data set, we want to assure you in some way that if there's data set 1 that has your data in it and data set 2 with your record removed, if I do a query of these 2 data sets, I should not be able to tell which data set contains your data, okay? So when we look at differential privacy, and differential privacy, I have another slide that discusses it, but think of this as access to the data through some mediator. So I'm querying, but I'm actually querying this sanitized data, and I'm gonna get some data with some noise added to it, okay? So I have D1, and I have D prime. And so if these 2 neighboring data sets differ by only 1 user, basically we're saying that the resulting query is going to be so close that you won't be able to tell which data set contains the particular record, okay? And I actually stole this from John. He has some great slides on differential privacy. He's our resident differential privacy expert. So if you guys have any DP questions, I say see him, after the talk. But this is one of his slides, and I thought it gave a great, explained it very clearly at a high enough level that we didn't have to actually get into the details of differential privacy. So basically what I'm looking at is I use several differentially private algorithms to generate these noisy data sets. I'm going to do some type of statistical analysis on these data sets that are driven by the use cases that the Kinsey researchers are using. And these algorithms, add noise in different ways. And so that is the partitioning strategy and, algorithms that I'm talking about. But all the queries are basically mediated. Okay. Are there any questions right now? So basically, yes. Rashif. Well, right now, this is all for me to determine what is useful. So yes, I do have the original records. So one of the goals is possibly, you know, I want to consider, can I get rid of the original records? And one thing that I think where I can do that, and we'll get to these results, is that if with studies, these behavioral scientists go through rounds and rounds in trying to determine what is the actual model that they should use to predict some behavior. You know, what are the variables or the questions that they should answer? So as they're forming this model, they may do some limited surveys and collect some data to refine their model and things like that to understand which features or variables are important for prediction. Okay, so in that particular case, I think that it would be great if we didn't keep that original data around, you know, and so because you know, it's not going to, if the model changes over time, then I don't actually need that original data. So what if I could store that data in a noisy form, you know, from the very beginning? So that's one of those cases where I think we may not need the original data. But with differential privacy, basically you assume that the original data is there. But people, the sharing mechanism is that I share through this querying interface. You can ask it certain questions, and that's, you know, that's how the sharing, but you never get a hold of the original data. Okay. All right. So, so I'm going to talk a little bit about, you know, the different algorithms that we evaluate. There are two sets of work that I'm looking at. One is by Li Zhang and her students out of Emory, and the other is out of Cornell by YXiao. And so with Li Zhang, she presents two algorithms. The first one is the cell-based algorithm, which is the basic algorithm that Dwork defines in her paper. And basically, it's like I'll add noise to each cell within the data set. Okay? So I add some noise to each cell uniformly, okay? And so the cell and the basic is what was provided in code that we got from the people who are doing the work at Cornell. And they add noise using the epsilon privacy parameter, you know, basically in the same way. The ad hoc algorithm out of Cornell, basically what it does is that it transforms the data set, the frequency matrix for the data set, into using a wavelet transform. And then it adds noise to this wavelet transform, and then it maps it back to the original frequency matrix. Okay? So that's the wavelet. The K-dtree partitioning, yes? Okay, so a cell would be like, let's say for an example, I have age. And my age range goes from 18 to 75. So the value at 18 would be considered a cell. But let's say I have age and gender. So now I have age 18 and gender female would actually combine to be a cell. So that's what I would say, you know, was a cell. How many females that are 18 years old are in this data set? And so that would be a cell. So as you have more variables, you look at the cross product of all of those, and each, you know, unique representation is a cell. Okay? So with regards to the K-dtree partitioning algorithm, this adds noise in two phases. Okay? And if we look at, in comparison to the wavelet, wavelet does a two-phase thing also. At first I transform this data matrix, and then I add noise to the transform matrix, and I go back. But what K-dtree does is that it takes its noise, its privacy budget, it adds noise to the original data set to create a synthetic data set. It takes partitioning indices from the noisy data set, and then it partitions the original data set and based on a parameter in the data that it's trying to preserve. And that parameter is entropy for the K-dtree algorithm. Okay, they also, I think, have an algorithm that uses variance, but what they're trying to do is preserve the overall entropy of the data set. So, and so then it adds noise uniformly within the partition, and a partition is made up of multiple cells. Now, what we're going to see when we begin to look at the results from the K-dtree algorithm is that the fact that they're adding noise twice, You know, and it's not that we're adding, you know, more noise in comparison to the other algorithm, is that I'm actually doing my partitioning based on a noisy data set. I'm pulling those indices from that noisy data set, and that amount of noise affects how well it performs when we're looking at the results, you know, the utility results, okay? So that, while it gives some hope for higher dimensional data sets, because it's trying to preserve some properties of the data, it's not there yet, because that, you know, partitioning based on a noisy data set is just enough to throw it off. Okay, so remember that as we are going on. So I've talked about, you know, why we're looking at this. I've talked about differential privacy at an extremely high level. There's a lot going into it, but I'm not here to discuss that. I'm more here to discuss, you know, let's, you know, do a use case analysis of a differentially private data set, compare it to the results that we got from the original data, and see how well we do, and see in what cases does it work, and where there should be some improvements. So basically I do a use case based analysis, and this is work that was published in 2009. And what they do is that they use a multivariate logistic regression to evaluate the likelihood that a participant reported an unplanned pregnancy, which is a binary outcome, and the likelihood of having unprotected sex in the last 12 months. And so this study was part of a study funded by the CDC because they wanted to understand what makes people engage in risky sexual behavior and the likelihood of unplanned pregnancy associated with this, okay? So this study had over 300 plus variables, but this particular evaluation only used like 9 of those, okay? So when I refer to my full data set later on, it's only with 9 of those. So with regards to the utility measures, there are 4 different utility measures that I use. One is just looking at variable distributions. First thing I want to do is understand how much have I changed the distribution, the proportion of females in the data set. Is it the same in the noisy data set? If I destroy these proportions, things like logistic regressions that rely on the probability of a particular variable occurring in the data set are not going to work well. So I begin with variable distributions so I can begin to say, okay, this is what the variable distributions look like. I don't retain utility in them because they're statistically significantly different. I don't expect logistic to actually perform well. So that's why I'm looking at variable distributions, because I want to understand why. If it doesn't perform well, why doesn't it? Okay? So I compare the results of the logistic regression. And so I do one sample t-test for the odds ratios. And see, what I didn't tell you is that with differential privacy, because I'm pulling the noise from a random variable, basically I create 25 differentially private histograms, and that's what I use for the analysis. So it's not like I'm using one noisy histogram and I'm doing this analysis. I actually do 25. You can do more. That just creates more data and probably make your results more sound. But I saw with 25 we actually got you know, pretty good results. So I compare the odds ratios for each variable level that's considered to be a predictor with the one sample t-test. Compare the original to the 25. The second thing that I do is that I create something called a p-score that looks at whether the significance of that variable level has changed, whether it has become insignificant if it was significant or significant if it wasn't. And so this is what I call the p-score. And I came up with this notion of a p-score when talking with the Kinsey people, because I asked them, when is the data not going to be useful for you? And they're like, what are you talking about? Because they have no notion of, let me perturb the data, let me add noise. What they want is to have the result to be the exact result, you know? So when you begin to say, I'm going to add noise to your data, you know, they become very anxious, okay? So I wanted something that would be conservative, you know? So what I allowed for was like 4%, you know, error. So if there was one out of the 25, you know, if there was a significant change in one of the 25 data sets for that particular variable, then I said, okay, you know, this is a good run, but anything above 1, then it's a bad run. So I'm trying to be conservative because they're very conservative, and they don't want, you know, they actually don't want any noise, and they don't know how to express, you know, what they consider to be useful other than exact. Okay, so that kind of explains the p-score. Okay, so after looking at the logistic, I said, well, let's look at other classifiers, you know, to determine, you know, do we get like better utility values, you know, with the classifiers. And so I have 8 standard classifiers. I'm sorry I didn't tell you exactly what they are and what they do in the paper. I just in light of time, I didn't go into this. But these are provided by the sklearn library with Python, so you can take a look at those and see which they are. And I use tenfold cross-validation to generate 10 area under of the curve scores for each classifier. And then I use a Wilcoxon sign test to compare the scores to those that were derived to those from the original data. Okay, so that's kind of what I did for classification. And the last that I did was feature importance. And with feature importance, what I'm doing is using like randomized trees to create this order of variables or features that are important for prediction, that are the strongest for prediction. Okay, and actually this gave the best, you know, results with regards to utility, and it makes it hopeful for me with regards to those beginning phases that the scientists go through in order to try to build their model to determine which features are important. Yes?
I just want to clarify how you measure the utility. So you do 25 runs.
Yes. Yeah. Yes.
And in each case you do a hypothesis testing.
Yes.
Right? And the hypothesis is like the mean results in coolant or something.
Yes.
And it can only fail at one of those 25 tests.
For the logistic on the p-score. Yeah. For the
hypothesis you are testing is the p-scores are equal.
The p-scores are equivalent, or they don't have to be equivalent. I can have at least one that is not the same. 1 out of the 25, that's what I allow.
But each time you check
each time I check that for the logistic.
And then what's the confidence level for each hypothesis?
For each hypothesis, the confidence level is I'm using a p value of 0.05. Yes. Well, the thing is, when you design the study, I think that's what I'm beginning to try to learn and understand. You know, the 25 will give you a more stable, you know, a result. And if you're designing a system, you know, that is going to be a query system, you know, maybe the result that you give them, you know, from their query, if they're doing a logistic and doing it in the way in which I'm doing it, by first creating a differentially private data set, and then from this differentially private histogram, I basically map it back to, you know, create a data set from that. If you're doing it that way, I would say give them more, you know, give them the 25, because at least they know that what they're basing this on, it is stable. It is more stable than just one, yes. Well, no, that doesn't mean that, because one thing I didn't explain is that I'm not doing this in an iterative fashion where you make a query and, you know, and you continue to make a query and you're using your privacy budget. What I do is that I assume that I know all the questions that you're going to ask, you know, of the data set, because I'm basing this on a study that already has been done and I know the questions that are to be asked. So I include all variables in the data set when I'm creating this differentially private data set. So it's not an iterative process where I don't know in the future you may ask something of another variable that I haven't included. So basically, I use the epsilon parameter, all the variables, and I just create 25 different differentially private histograms and then reconstruct a data set from that and then do a logistic on it, or also, you know, run one of the classifiers on now this noisy data set. Yes, John?
The question is, you generate 25 differentially graded histograms.
Yes.
Each one of them generated with parameter epsilon over 25?
No, 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 no. Each one of them are generated epsilon.
But then the whole algorithm, why is it epsilon differential?
Oh, no, no, no. Oh, okay, I see what you're saying. Okay, now I get the question. Okay, yeah.
I think you are using 25 to understand.
Yeah, I'm using 25 to understand that, but now
In practice, you give one.
yeah, in practice you give one, yeah.
The distribution by taking many samples from.
Okay, yeah. Now I understand the question that you're asking. Okay. All right. So so let's talk about a little bit about the data. The full data set has age, employment, gender, income, relation. This scaled module. This particular question is from a scale module, and its use of same-sex products causes arousal loss. And remember that question because it's going to come up again. And this one, risk of pregnancy inhibits arousal, and that's CIS-8. And what I can tell you now about CIS-5 is that out of all of these variables, the disagree level of that question was the one that was most prominent in the data set. It's the one that was most, the biggest response. Okay, the most frequent response in the data set. Okay, so, and also we have these two variables: had unprotected sex in the last 2 months, ever had an unplanned pregnancy. And these are our outcomes that we're trying to predict. Okay, so also because of the issue with dimensionality, I basically created some reduced data sets that were not in the a part of the original study, but just to try to understand you know, how utility changes when I'm looking at fewer variables and I've reduced the dimensionality of the data set. Okay? So income and use of unsafe sex products, and then relationship status and risk of unplanned pregnancy and ever had an unplanned pregnancy. And I talked with my collaborators at Kinsey to determine which two would be the most likely that they would use in order to determine what the reduced sets should be. Okay, so now I'm going to get to the results. And basically with the results, I'll start out with data distributions, okay? For the full data set that I showed, none of the utility was preserved. None of the variable levels were preserved. As far as the proportion of a response in the original data set in comparison to the noisy data set, no utility at all. And I show this slide to kind of give you an idea of why. Because this is the original age, and this is the age distribution for like the best, for the best data set that we had. And when I say best, it was based on the effect size, with the smallest effect size. Okay? And so we've kind of just totally changed this. Yes? I am sorry. I didn't include that in this, but I do have epsilon values for the other ones, but I didn't do it. And I think this one, I know this is with the K-dtree algorithm. So in addition to epsilon, what we will need to understand is what is the entropy threshold that we're also using in that. And so, but this was the best one. I'm sorry I didn't keep that information for this slide. But yes, John. No, basically it was from the full, you know, with all the variables, and I just pulled age out.
This is like just a subset.
Yeah, this is just a subset, and I just pulled age out. Pulled age out. Okay.
So it's one dimension, right?
Yeah. Yes. And we actually put them into, you know, ranges. Okay. Interesting. So if none of my variable distributions for none of the algorithms, the 4 algorithms that I use preserve utility, I would expect that I would get for the logistic, I wouldn't preserve utility for anything. That's what I would expect because I've destroyed the variable distributions. They're all significantly different, but that's actually not what happened. Okay, remember when I told you to remember that variable sys 5, the one that was the most frequently responded answer was disagree to do safe sex products cause you to lose arousal? And that's the variable that is actually preserved. And this is the effect size 0.020 using Coins D to actually determine effect size. And it's for an epsilon of 1.1. And the entropy threshold is 0.682, which is the entropy threshold for the original data set. Okay? So this one blip was the thing that actually utility was preserved here. And you know the reason that I think that it was preserved is because it was the most frequent response in that data set, and it was preserved. Okay, so the thing is, so I wanted to, I was talking with people about, how I look at logistic and evaluate whether it, utility is preserved or not. And there were some people that were concerned that I was being too conservative with the p-score. Like I should allow more error. Maybe I'm being too conservative. 1 out of 25 is too small. Okay, so basically what I did was went up to 6 out of 25. And that would give me about 24% error. And what I got is that there was no change at all as far as utility. So if I was being too conservative, that would mean that my utility should go up with the logistic, if I allowed there to be more error in the p-score. But it didn't. Okay, so this is for the K-dtree algorithm for the full data set where only one variable level was preserved. Okay, and this is a data set this is an algorithm that's trying to preserve some property of the data. Yes?
I find it a little perplexing that with the increase in epsilon, as you said, nothing is happening to the increase. Did you try going below 0.1 or higher than?
Well, I didn't try going above 2.0, but I think the reason that we are not seeing an increase in utility also has to do with the fact that we're dealing with an entropy threshold and how we're trying to partition the data to preserve this. And so what I find and what I'm going to show you in the later results is that for the K-dtree algorithm, that the best results are coming when the entropy threshold is set to the original entropy threshold of the entropy threshold of the original data set and above. And above because we have this noisy way of partitioning the data. Okay? So I didn't go below, that would be adding more noise, and I didn't go above 2.0. And we see that even as we increase, it's not doing anything. And I'll show you even for the reduced data sets, when I look at the p-score, we see a little bit, there is some change, but it kind of levels off. And I'll show you that for 2 different algorithms. Okay, so let's look at the classifiers for the full. So this goes to what I was talking about, with regards to using classifiers, tree-based decisions that are not, oftentimes the decisions in the classifier are made based on a relationship and not based on the exact probabilities of something occurring in the data. Okay, and so we actually see better performance. You see the basic, ad hoc, and cell performing about the same. Okay, and so I get 40% of the actual runs are predicting at the same level, okay, as the original. And so basically when I'm looking at the classifiers, I'm looking at how well does the model predict on the noisy data set in comparison to the original data set. And I'm showing that, you know, and here you see my K-dtree partitioning is not doing as well, but as we increase epsilon, like you were saying, we're reducing the amount of noise, we actually see that there is an increase. But what I wanted to do, because with the partitioning algorithm is actually, there are two parameters, there's epsilon and entropy threshold, was to break that out so we can look at it. Okay? And so what we see is that this is for I have a different line for every entropy threshold. And we see that when the entropy threshold is 1, and when the entropy threshold is like 0.9, we actually get a better value. So this is actually greater than what the original was, which was 0.682. Okay. So we see that for those values, when the entropy threshold are actually greater than the original, we get similar performance to the other algorithms that don't have a partitioning strategy. So they're performing at about at 40%, and we get a little bit above 40%. Good utility. Like the model predicts as well. Okay. So when we look at feature importance, and so we get similar results, but with feature importance, we see that the K-dtree partitioning algorithm begins to perform a little bit better as we reduce the amount of noise. And so when we look at K-dtree for the full data set on feature importance, and you begin to see that when I have the best performance is coming when entropy threshold is 1, and we have higher values for epsilon. Okay. But the takeaway from this is that even when the variable distributions, I had no utility, you know, no utility preserved with variable distributions. I've totally destroyed the variable distributions. I still get significantly better performance than the logistic when I'm using classifier-based models as opposed to the logistic. Okay. Tree-based classifiers as opposed to the logistic. Now when we look at the variable distributions for RS1, we get actually significantly better performance. And so what we're seeing for the ad hoc basic and cell-based algorithms is that there are times when 100% of the time we're preserving the variable distributions with that. And we have K-dtree's performance is not performing as well. But we'll look and see when it performs better. Yes?
Sorry, could you just remind me what a good run is? A variable that's significant.
With a good run, that's when the proportion of answers for a particular question or within the data set is the same proportion in the original data set and the noisy set of data sets.
With a question, an example of a question would be like, is gender related to fill in the blank? Is that
With variable, the question would be male or female, and you would check that. So if I have 25% females in my original data set, I want to have 25% females in my noisy data set. That's basically, you know, what variable distributions is, what I'm trying to measure with regards to variable distributions. I want to see how much I've changed the overall distribution, which will give me an indication of what kind of performance I expect for logistic and those other things. Okay, yes. No, because I can go back and tell you exactly what I'm using to measure what that is. I think we're doing a Pearson goodness fit test for that. Okay. So Here we get, you know, up to 100% for some of them. And so I wanted to look at K-dtree to see when it performs well, okay? And so when the entropy threshold is set to 1, that's when I get the best performance. I start out with epsilon being 0.1, and even when I get to 0.4, I get 80% of the of good runs with variable distributions. So while it looks, it doesn't look good here, we have to look at the actual parameter values where it's performing well. Because remember, this is being, I'm partitioning and I'm trying to preserve some property. Okay? And so when we look at the, oh, I put p-score in the wrong place. Where is the logistic for this? RS1. For some reason. Okay. Okay, variable distributions, K-dtree. And for the p-score with K-dtree, I think I missed a slide. I'm sorry about that. I was going to give you the logistic, but I don't have it actually in here. But what we see, instead of having the actual logistic scores, is that this is for cell-based and this is for the K-dtree algorithm. And so as I allow for more error, what I see is that, and the purple is the one that we're using as the threshold, okay? And this is actually no error. And so I don't get significantly, you know, better performance, you know, as we increase as we increase epsilon and as we increase the amount of error that we are allowing. Okay. And for K-dtree, we don't see any change at all. There's a little blip here. Okay. And so for the classifier results for RS1, we see something similar. And where 40% are actually preserved or good runs. And with the K-dtree and the classifiers RS1, it's the same thing. When I'm above the entropy threshold, that's basically what I'm getting. And then when we look at the feature ordering, we see something that is significantly better. And basically, we know that feature importance can be preserved in a lot of cases. And for the K-dtree, where it says that we're about a little bit above 40% here for, you know, all values of epsilon, we can achieve above 60% when the entropy threshold is 1. Okay, so those that kind of like gives you a summary of the results. There were also, I had another reduced set that I didn't include the results for because basically we saw similar patterns as with the previous results for classification and everything like that. With the reduced set 2, those results were actually better than reduced set 1. And I think just because of the nature of the questions and the frequency of the answers within the questions, they had a stronger presence in the data set. And so we had more of those being preserved. So the majority of the utility preserving levels are for the reduced sets, and this indicates that dimensionality is definitely a challenge. So when I have higher dimensional data, I need to have, you know, a larger data set, you know, and so that can be a possible, you know, issue, the way I'm trying to partition the data, especially if I'm doing it with a noisy partitioning, then that is definitely affecting, you know, the results, yes. The data set size, I had over 6,000 records in this data set. So over 320 attributes in the original data set, but we didn't create a noisy histogram for the 320. It would take an extreme amount of time if we could ever get it to stop. So our full data set that we considered were only like those 9 variables out of that data set. K-dtree performs better, and when I say better, for the full data set with logistic, basically what we saw is that we had one good run. That's one variable level, that was actually preserved, and it was the one that most frequently occurred. And I hope that this is promising. Promising because the researchers really need something that can help protect the data, especially for sharing purposes. Having an entropy threshold at or above that of the original data set is a strong predictor of utility preservation. Okay, so for the K-dtree partitioning algorithm, if my entropy threshold is at or above, then that's when that algorithm is going to perform the best with creating or generating a differentially private histogram that is going to preserve utility. And, I think I had, my discussion questions were, one of the things that I still don't understand, and the researchers don't understand this, is what amount of error is acceptable to data collectors? I don't know. And that's why I did the P-score, and I tried to do something conservative because I knew that they were conservative. And, is it a change in significance level? Is it a change in the strength and the odds ratio, but not the overall order of the strength of the predictors? This is a question. This is a question that I would like to, get an answer to. Because in order to design something that would be actually useful and usable by the researchers, we need to know this. So in order to know how to present this information, to the researcher. So that's basically, all that I have. If anyone has answers to the utility question as far as what is useful data or wants to talk about, what's useful data, then, I would come and talk to me, because if you have some ideas around that, that would be great. Another thing that is coming, the way I did this is I basically created a noisy data set. But there is work out there now that instead of, using this noisy data set and then doing a logistic on a noisy data set, basically what they do is perturb the output of the logistic itself. At the time that I was actually doing this work, there was one particular algorithm that I had in place, but because the algorithm, the way they did a Taylor expansion in order to approximate the logistic, even on the original data set, the logistic was so different from what a researcher would get by using something like SPSS. And that's what they're using. Because even on the original data set, it was so different, then they were, they wouldn't accept it. And that's why I didn't include it in the study, because, it wouldn't be a way for me to do a fair comparison between, the other algorithms. But I learned that there is new and improved algorithms out there for adding noise to the classifier result as opposed to adding noise to the data, but I haven't tried those right now. But I think there was a question. Okay, and so this project was funded by CACR, which is a security institute at Indiana University, by the National Science Foundation through the Text Anonymity Project, where Chris Clifton of Purdue is the lead PI on that. And I want to thank my collaborators again for their contributions to this work. And if you have any more questions, I welcome. I can stick around and talk with you about that. But thank you so much for having me.
Please, if there are any questions, please go ahead. We'll discussion right now.
Okay. Okay. Uh-huh.
So, is there, have you looked into whether or not that is happening in estimating the data, or?
No, I haven't, and I think I'm trying to understand what you're saying. As far as, are you saying that basically I may have artificially high good results on variable distributions?
Not on the variable distribution. You would give me a data set.
Okay.
Say is unexpected pregnancy associated with smoking and age, and I have a point estimator for smoking.
Okay.
And then a standard deviation estimate for that.
Okay.
And say, hey, great, my point estimate is like 2, and it has a small standard deviation, so I say it's significantly related.
Uh-huh.
But because you're adding noise, it might actually, that my standard deviation will actually be larger.
Okay.
And so it actually shouldn't be significant. So I think that the inference performed on the estimators, or the inference that the scientists will be performing, might not be accurate.
Oh, yeah, yeah, yeah. Oh, that, and I think that's that becomes, part, of the issue with regards to adding noise and trying to understand, can we, will this data actually be useful anymore? And I think that's why you see poor performance with things like the logistic, because now I can't really, say everything that I get is statistically different from the results with the original data. And so I don't get the case, and I think what you're saying is that on the noisy data, I get something that is misleading.
You would be more confident in your results than you should be. So your confidence intervals would be smaller.
Okay, and so what I haven't looked into that to say, well, I got this as a good result here. Is it actually a good result? But I'm comparing it to the original, to the original result, and using statistical tools to compare my logistic to the original. And so I'm not sure if I would encounter that, because I'm using my original result on the original data as the basis of comparison. Now, if, let's say I wasn't doing this and I just made the assumption that, this is a good result and I'm doing it on noisy data, I think that I would definitely have that problem. But because I'm using my original result as a baseline, I'm just trying to see how it compares to the original. And if it doesn't, then, then that's the issue. So I believe that if it's a good result, that I say that I preserve utility. I believe that result because it's in comparison to the original. If I didn't have the original, then I think I would have a problem. If I was just trying to make an inference on noisy data, I would have that problem that you're talking about. Yes.
I think it's great that you're trying to take differential pricing applied to the real world situation. And one related question I have with regards to you talking about what is a good level of error is, how did you convey what epsilons are good to McKinsey? Have you even gotten that?
Yeah, I actually, I talked to them and I, explain things to them. And as far as, the trade-off, but we haven't gotten into that discussion about if you want more privacy, then you need a lower value. I think what they would be satisfied with is that if I have improved privacy and decent utility and good utility.
But what improved is what you say improved is not something that they understand, so they trust you on the...
Well, the thing is, that's why I actually talk with them about what was good and why because they weren't able to articulate what was good utility to me. But I sensed that they were very conservative. Okay, so I tried to be as conservative as I could be with regards to the P-score. And that's why I set it for very low error. I only allowed, 1 of the 25. And what I saw with results is that it doesn't even matter because I'm not getting an improvement there. So there is the ability to get lost in translation from what they want and what I perceive that they want from our conversation. But what I perceived, and I can't really express mathematically, you know, is that they are conservative and they're very concerned with the outcomes. They want it to be exact. By adding noise, you don't get that. So if you're going to use some other type of technique, you may lose some meaning, you may lose something else, and you may not get the guarantee that something like differential privacy would give you. And so that becomes part of the conversation, you know, with them. But I understand what you're saying. That is the challenge for me. And they couldn't tell me that 1 out of 25 would be good. I don't think they would say that. I just said I'm going to be conservative because what I'm sensing is that they're very concerned. And so, no, there is no formula from trying to extract that information from them, you know. And so whether they agree with my 1 out of 25, that's something that I have to go back and talk to them about. But I can also show them the results that say, hey, you're not getting any improvement even if you go up. So, but I understand. I'm trying to figure that out myself. Yes, John.
So could you say something about sort of how and why you chose the particular algorithms that you experimented with?
You know what? One of the reasons, like the K-dtree one, because they were doing a partitioning and it was said to be better, you know, for higher dimensional data because they're trying to preserve some properties of the data. That's why. I knew I was dealing with high dimensional data. Okay. The other ones, the basic, you know, the cell-based, you know, they are just the regular, you know, DWARC-based ones. The wavelet was an algorithm that came after I started doing the study, you know, that was published after I began looking at it. And, you know, it was recommended that I try it. Now, wavelet now is good for range queries, not necessarily, you know, for this. But I said, you know, it was available. Let me just do a comparison. And it doesn't perform, you know, for this type of data is not giving me a significantly worse performance than the other algorithms. So that's how I chose. And I wanted to do the, you know, the one where I'm adding noise to the actual logistic, but it wouldn't have been, I couldn't do a fair comparison with that. So if I had something that gave me you know, more accurate results, you know, that where I perturbed the outcome of the classifier, then I would have used that in the comparison. But this, at the time that I did the study, these were the algorithms that were actually out there and available and, you know, and I could begin to use them immediately. And I was, you know, also collaborating with Lee. That's, you know, why I was able to, you know, get her algorithm and her code quickly. Yeah, there were the number of cells is like 9 times, I think, because we have aged by 2. It was about like 9 times 30. I actually have it. I can look it up in the paper and tell you actually how many different dimensions it was.
Right. I mean, there are algorithms from literature that sort of, at least in theory, kind of come very close to sort of the optimal error you could get under differential privacy in kind of some measure. So I don't know how well that measure corresponds to what
okay.
people can do, but you know, the main kind of drawback of all of those methods is that the running time kind of grows with the number of cells.
Mm-hmm.
You know, can grow exponentially.
Mm-hmm.
Exponentially with the number of attributes.
Okay.
Working with something where the number of, like your algorithms are also doing something that kind of iterates over all the cells.
Yeah,
Right?
yeah.
Basic histogram.
Yeah.
To count, like, explicitly
Yeah.
count each cell. So it seems like, you know, those methods, even though kind of you know, in theory the running time is unacceptable, like for a problem of this size.
You say that it's doable.
I would say it's doable, and I mean, there are.
But and the thing is, even with the K-dtree partitioning algorithm, you know, Li Zhang told me, oh, we got far better utility on the data set that we used, and you know, than what I'm getting with this particular data set. You know, so she was like, there's something going on, and I started to ask her about, you know, well, what are the characteristics of this, you know, of the data set? And I don't think it was as high as, you know, as far as dimensions as this one. So, I mean, one of the things with these algorithms that you're talking about that do, you know, theoretically better, you know, it'd be interesting to look at them and I guess either implement them or use the code that they have to see whether they actually, you know, do better. Because I know that Adam Smith has one, and it's more about using some type of point estimation approach to get the, you know, but I don't think that there is an implementation of what he's done.
So that's actually, I actually have one for you.
Okay.
So that, but that's not sort of what I'm advocating.
Okay.
That's for kind of the problem that, I mean, that's for a different version of the problem.
Yeah.
You just want to get the logistic regression.
Yeah.
So
Yeah.
And I agree that getting kind of like a synthetic perturbed data set is like a really well-motivated goal. So I'm only talking about algorithms that can actually produce, you know, data sets.
Okay. Okay.
But even there, so like there are some experimental evaluations of those algorithms. The notions of utility they use are somewhat different, but also seem kind of non-trivial. So
Okay. And then my notion of utility is based on what the scientists would need. And so it's not based on anything else. It's like, what are the outcomes that they're looking for? What could actually be useful for them? And so there are a whole lot of, you know, and for, you know, and I don't know how those algorithms would perform with regards to the utility measures that I'm actually using. So this is basically for the application of the scientist. You know, like how would they use this data? What would be useful to them? And how maybe they may use some other kind of classifier to do some of the things they're doing. And so that's the whole goal and the reason for doing this, and not, you know, I'm not using a utility measure that some of the others are using because I'm looking at what's going to be helpful to them.
right, so that I completely appreciate. I'm just wondering if starting with kind of the algorithm, like, given that it's sort of hard to prove like theorems about kind of the particular utility measures that you're using, like you tend to prove theorems about kind of simpler, you know, easier to work with quantities, but that doesn't mean that like I was curious, for instance, if the algorithms that you chose, the types of guarantees people prove are like more tailored to what you're doing? Or?
No, the thing is, like Lee's algorithm and the work out of Cornell, the guarantees with regards to privacy or utility, which ones are you asking me about? Oh, okay. They had some utility measures that I did not use. Okay, with regards to privacy, they prove that this is, you know, differentially private. Yeah. So, but I think, yeah.
There was the L1 norm out there. I think, but the challenge here is, even with 9 dimensions, I think they have maybe 500, 600 cells.
Yeah.
Maybe more than that. And there are 6,000 people on there. So each cell will have few counts.
Yeah, a few counts.
Then it will become like a random matrix.
So this is sort of why I wouldn't use I wouldn't attempt to get a histogram that has a small L1 distance to the true histogram. I mean, I think that's like you can prove. I mean, that can't be like done.
Exactly. I think that's the issue, right?
Right,
You
so
can't get the histogram with 9 dimensions with 6,000 samples.
Right, but like for instance, so like what if I had an algorithm where I guarantee that you know, the histogram may have large L1 distance, but if you do you know, a logistic regression and a subset of the variables, you'll get similar block likelihood.
I think that's what.
I mean, that's the kind of things people.
I think you need to perturb the model directly instead of trying to.
Yeah. So I guess one thing, John, I'm trying to understand. So what is it that, you know, what is it that you would like to see? I've heard a couple of things. That why don't you use the utility measures that the other people used? And I'm trying to understand.
So that's like not what I'm saying.
Okay.
What I'm actually saying is that there are algorithms that admittedly were not designed to give sort of the optimal results under your utility measures.
Okay.
But sort of
Okay.
close to it.
So
I'm curious what, just because like the results aren't, theoretically proven for like the exact utility measure that, I mean, not even just for you, but like for like, you can't prove a result saying like, the scientists at the Kinsey Institute are X units of happy with this data.
Uh-huh.
It's not something you can quantify nicely.
Mm-hmm.
But I'm just wondering, like, I was just trying to get a sense of like what made like these particular methods sort of good candidates in your opinion, as opposed to the ones that are kind of more like theoretically are sort of more powerful. Or
I think these methods were more common in the database community. I see. That's the one.
And I would agree. I would agree that they are more common in the database community, and also with the wavelet one. I wouldn't even say it's not a good candidate for the type of data. It's more for.
in hindsight, it doesn't work very well.
Well, no, not even in hindsight. I knew this beforehand, but as far as as I've been going through doing this work, one of the reviewers insisted on us using this. Okay, so I mean, and because of that, I mean, because this is based on range queries, and it works better if your range is large, and our range is not. Because a lot of the variables, there's 6 possibilities, right? And that's it. Agree, strongly agree, disagree, and stuff. And so you don't get a large range there. And so it's not a good fit for that. And although it's not a good fit in comparison to some of the other algorithms, it actually, performs, similar. So, but yeah, as far as, that the cell and basic, they're basically the same, just regular dwarf. The other ones, I would agree with Murat. They're not as well known in the database community. And so, and they basically live within the theoretical community. And if I hadn't, like even with Adam's work, I wouldn't have known about it if I hadn't been, talking with some theory people. Yes.
There's some more work coming out of AT&T by Graham Cormode and all.
Mm-hmm.
They have some theoretically motivated algorithms, but they have done extensive experiments.
Okay.
So I would suggest definitely look at that, and a lot of that is about histograms and about kind of partitioning.
I think it's clear that if you're doing 3 or 4 dimensions, and then very large datasets, we have done some simulation for Gaussian extreme models and so on, then it will work. There is no doubt. I don't know how many dimensions they have, but at least the current result there, if you have 10 dimensions and 8,000, I don't think anything exists. Maybe it's about there. I don't know most of the theoretical work.
So it's just like, I mean, so there are like empirical papers based on some of the kind of more theoretically like favorite algorithms, and so they, for instance, they'll generate. I mean, they sort of use it for things kind of outside what you normally prove about it, but they can generate like synthetic databases for 16 dimensions, let's say. I think they're using like the adult dataset. Familiar with this? So it's like 16 dimensions, about 30,000 people.
So I think basically what you guys are saying, and kind of what I'm hearing with regards to this working, for something like Kinsey, for the kind of stuff that they want to do. You need to have a significantly larger data set with regards to the number of participants.
I'm not totally sure of that.
Yeah, but larger than the 6,000. It's yeah. But so and I can test that out by just generating just replicating some of the rows within this data set and just seeing, do I get better results, and keeping the proportions basically the same. Just replicate some of them and just make the data set larger.
Oh yeah.
For an experiment. Yeah. Let's just replicate and see how. Yeah.
Also just trying some like given that the fact that the number of cells is kind of manageable, it just seems to open up like a lot of algorithms that you could try.
Okay, so send me some of those algorithms.
Okay. Yeah, sure.
Okay. Okay.
One is, you talked about going 2 ways. One is that you add noise to the classifier,
Mm-hmm.
and the other is you want to construct a synthetic data set. So did you run any one of the standard so you could just go.
Oh yeah, yeah. This is the original was a standard R logistic regression.
Okay. So
That was the logistic regression was the standard R.
no, I mean a differentially private logistic regression. There's also a library out there. So there was this
Oh.
original differentially private regression paper that came out in 2008, and then I learned that maybe last year they now have an R library.
Okay. Oh yeah. Okay. I didn't run that one. We did the one. It was called. It was a functional mechanism. That was the. It's a newer result. Okay, yeah, and I know the authors of that, when I contacted them and I told them about, how their results on the original data was so different and I couldn't use it, they told me we have a new one coming out. And at that time, I think it was under review. And no, I didn't know about the...
This is like a concept.
Oh, okay, okay.
But it's been around for a while now, and they also have R code.
Okay, yeah.
I guess if we chat later today, I can describe like the basic version of this.
Okay, yeah. Yeah, I think it's about time for us to go, but